My name is Gamsara, and this is BonsaiKV, towards fast, scalable, and persistent key value stores with tiered heterogeneous memory systems. So this paper was published in VLDB 24. Here, so key value stores are essential for high-performance storage, and they're known for speed, but they're often limited by DRAM in general. So for current in-memory solutions, scalability without compromising the cost is needed. So the DRAM is expensive, but it's very hard to scale. So it cannot meet the large-scale application demands in terms of persistence, for example, or capacity. So these systems usually utilize slow devices for persistence and capacity, but at the cost of a lower performance. So in this paper, they focus on three challenges mainly. The first one is that the DRAM is not only faster than the NVM, but also has lower capacity. So making this resource or the DRAM resource precious in this system. So in production, they say that 800 gigabytes of Facebook social graph data consumes 183 gigabytes of DRAM to index within RocksDB, which is pretty much 1/3 to 1/4 of the data is indexed. So it's very important for them to reduce the memory consumption or footprint of the index, because these large, I'd say the size of the index is very large. It consumes a very big memory footprint in the server. So a common solution to the problem is hybrid indexes. But the naive solutions are usually bounded by the expensive non-volatile memory access latency and its low bandwidth. So their first task is how to reduce the memory consumption without degrading the data indexing. The second challenge is related to the non-volatile memory bandwidth contention. So the non-volatile memory is notorious for having low bandwidth and low parallelism on top of that. So the traffics coming from different data flows are going to interfere and compete for the scarce bandwidth. So persistent indexes especially make this issue more prominent because they handle everything in the non-volatile memory. So another small detail that in production, for Facebook again, they say that the value size is usually very large. And these very large values from 3 to 100 kilobyte come in a burst request manner. So they create this contention because of the nature of the workload and the size of the value. So, which is basically the worst case scenario, persisting large size requests in such a small time. So that they need to address this non-volatile memory congestion for data persistence. So the last challenge is scalability. And here it comes on two levels, the channel level parallelism and then the node level. So the channel level parallelism is usually handled with striping. And they say that the current available striping techniques are too coarse-grained to get the benefits. And for remote node access, they're usually handled through either delegation or replication, but both these solutions still have some issues such as centralized delegation overheads or the write-heavy data coherence protocols that are not NVM friendly per se. So they aim to solve this issue, which is how to scale to multi-DIMM and multi-node systems efficiently.
It's not quite obvious why we have a problem with the traditional striping.
Because here, because they say that smaller striping size, like I mentioned here, makes smaller instructions, and these smaller instructions are more likely to be sent to multiple channels. So if we stripe data entry to 2 stripes, we only use 2 devices, but if we stripe it to 6 devices, then we parallel over 6 channels. That's the purpose.
So the main problem is a granularity problem?
Yes, in terms of striping.
If it's too small, then...
If it's too small, we don't utilize these multiple channels that we have. So to achieve this or to tackle these 3 challenges, they set 4 design principles. The first one is that they index over 2 distinct memory tiers. And what they do is they offload part of the indexing to the non-volatile memory. So usually we perform the lookup in the DRAM, and then we find that location, and then we retrieve the data from the slower device. But what they do is they split this indexing lookup. Half of it's going to be done in the DRAM, and then another part of it is going to be done in the non-volatile memory. And they say that this offloads a lot of metadata to the non-volatile memory and compensates for the DRAM's small capacity. So you might say, okay, if we do some of the or part of the indexing in the non-volatile memory, it's going to be slower. But actually, it's not, because they do an optimization where they bring some metadata back to the DRAM for faster lookup. So I'm going to talk about this in detail a little bit later, but this is just an overview. So the second part is that they uncover a strong correlation between the data persistence size per thread and then, or the total data persistence size and the non-volatile memory congestion. So they do this through an analytical model, which I will explain in detail. And from the conclusions of this analytical model, they are going to propose some congestion control mechanisms that are going to regulate the data persistence granularity. And by regulating this granularity, it's going to address the memory traffic interference and the bandwidth contention. So the third one is a novel key value data striping design that exploits channel level parallelism. So logically, they're going to aggregate a number of key value pairs to each the management, so within one address space. But physically, it's going to be striped and spread across different memory devices. Then the last one is the NUMA level parallelism. So we know NUMA architectures pose several challenges for key value stores in terms of non-uniform memory access properties and slower remote accesses. So what they do is that they localize the data writes, and they adopt an adaptive data replication mechanism that's going to alleviate this remote memory read costs. And the data coherence is going to be achieved with the write optimal self-invalidation protocol. So write optimal, yeah, means like self-invalidation. So the replicas will self-expire and self-invalidate, but they will not block the incoming rounds. Moving to the next round is detail. So they exhibit a 3-layer hierarchical system architecture. It's going to span across 2-tiered memories and is going to be equipped with multiple channel independent DRAMs and NVMs. So they carefully tailor this data storage format in each layer. And the basic units here are, first is going to be the index node or the inode. So the index layer here, they implemented it as mass tree. This is basically a leaf node of mass tree. And then the index, the persistent log here in the log layer in the non-volatile memory, and then the data nodes, which are named D node. So the 3 layers here, they cooperate to serve 4 types of key value requests, which are get, put, delete, and scan. And these requests are first issued here to the index layer, which uses the key to perform what they call is a collaborative tiered lookup. So it will first find the associated index entry in the DRAM or the inode. It will read the inode and then perform the remaining indexing in the log layer and the data layer. So I have a little bit of detail later. Just for now, it's going to perform a lookup, find an inode, and this inode is going to help us to locate the data either here or here. And then for puts and deletes specifically, or data modification in general, they create new logs in the log layer. And then the delete will have a tombstone value in the log. And then after the log has been created in the log layer, later they're going to checkpoint it to the data layer. So after it has been checkpointed to the data layer, the key value data is moved from the logs to the new node. So it's NVM to NVM movement. And then the associated index entry. So first we created a log and we created an inode that's going to point to this value in the log. But after we checkpoint it, we're going to perform an indexing tier modification, means okay, we moved this node or this value to the data, so we have to reflect it on the DRAM index. And then finally, the key value pairs stored in the D node are going to deliver the access parallelism with data striping scheme.
So I have a question about the overall architecture.
Uh-huh.
So it comprises DRAM and NVM only without
Yes.
any flash-based storage.
Without storage.
Mm.
But the NVM is used in persistent mode, so NVM will persist the data. So we move to the index layer, which is the top. So this collaborative tiered indexing, it aims to resolve a trade-off between DRAM consumption and some indexing performance, right? So going level by level and starting at the top, they designed this low-cost shim layer between the DRAM and the NVM indexing. And the purpose of it is reducing the DRAM consumption by, like I said earlier, offloading part of the DRAM index to the non-volatile memory transparently. Due to this index offloading, the whole index task will be split into two parts.
Question.
Yeah.
What's the primary purpose of splitting the index lookup into two different parts? One is done in DRAM, the other one is done in.
It's because they want to reduce the amount of a resident data in the DRAM incurred by the index. So we want, yeah, so we want the index to consume less DRAM capacity. So we're going to send some of the metadata.
Here's the memory required for the DRAM index side.
Yeah, exactly.
So some of those, the lower part of the index should be chunked out.
Yeah, pretty much. So the shim layer is composed of a list of volatile inodes, and the inode is responsible for tracking the key value pairs that are either stored in a log or in a data layer or in a D node. So starting, the thread is going to search for the plugin, search the plugin DRAM index to find and read the corresponding inode. And then it's going to perform an inode lookup is going to search either a log or a D node. So it's going to use this fingerprint mechanism for a fast lookup. And the fingerprint is a 1-byte hash value of a key similar to FP3. And it's going to compute the key fingerprint and check the bitmap for this. It's going to tell us a log ID, the fingerprint. And we're going to the bitmap to check if this log ID is valid or not valid. And then if it is valid, we find those log IDs with the same fingerprint and we pass them to the non-volatile memory indexing tier. So if we find the log IDs, like I said, if they have the same fingerprint, then we pass them to the non-volatile memory indexing tier. And
it just works as an guidepost to
kind of, yeah.
Whether your lookup should go to this log area.
Yes.
Or that area.
Yes,
right?
yes.
Okay.
So the log region is going to organize as a linear array. And then given a valid log ID, the NVM index is using them to index the logs in an array and compares the key with the requested key. If there's a match, then yeah, returns the key value. If there's no match, then it's performed in an associated D node.
So locally speaking, we can say this architecture just replaces flash-based storage with the NVM and further to look up data from log and data is not that rare in database systems. If so, what main contribution in this work, in this architecture?
This layer or the shim layer is a transparent way to kind of like transition between the lookup in the log and the lookup in the data. So from the DRAM, and then we transparently move.
Transparency direction, that's it.
Yeah.
So they can look up data, not differentiating if whether data resides in DRAM or NVM.
The DRAM lookup does not directly take us anywhere. So it transitions us to either a D node lookup or a log lookup.
That's the main role of the shim layer. Transparent in direction. Whether you have to go to log layer or data layer by looking at the fingerprint or the D node ID.
Yes.
So in this architecture, shim layer is their main contribution.
Yes, pretty much.
Sort of.
So moving to the log layer specifically, it uses a log structured method. So there's an array, but in terms of like persisting these logs from the volatile space to the non-volatile space, it's kind of in a log structured method with one layer, we could say this. But the non-volatile memory small bandwidth prevents this fast data persistence. So from now on forward, I'm going to present the analytical model to understand the non-volatile memory congestion regarding to the log persists. So in this figure, we can see that each CPU here is going to have a log region or a log buffer. So here we have N and G. So N is the number of threads in general, and G is the data persistence granularity. So how much data per request is each CPU going to persist? And then right now with modern out-of-order execution, we can support issuing multiple memory requests simultaneously. So the memory is going to query the L1 cache, and if there's a miss, it's going to put the request in the line fill buffer. So why this is relevant is that assuming that the CPU allows a maximum K outstanding memory requests. In this paper, they allow, I think, 12, if I remember correctly. And then the cache line size is C. They define the data transmission rate, which is DTR, without any granularity restriction as V. So DTR in general is V. So the DTR VG, which is of a certain data persistence granularity, is the data transmission rate is defined as the minimum between the granularity and maximum outstanding request times the cache size or cache line size over the maximum outstanding requests times the cache size times V, which is the data transmission rate. So why they do this is to go towards the total DTR, which is the total data transmission rate of N threads is pretty much VG times N. So how much is each thread or each CPU going to issue, or what its DTR is, and then how many we have. And from this, they also define a data service rate, which is the maximum data transmission rate that the non-volatile memory medium can guarantee. So from this model, they draw two conclusions. First is that the data transmission rate is proportional to the data persistence granularity. So if we raise this granularity, then the data transmission rate is going to go up to a certain limit. So the thread with the larger data persistence granularity, so if the line fill buffer or other buffers like a write priority queue are populated with this request, means in their definition that this thread has a higher priority. This is going to be serviced first. So they verify this experimentally, and the experiment creates two concurrent running threads. We have a low priority thread that's going to run at a fixed persistent granularity of 256. And then we have a high priority thread here in blue, which is going to have variable granularity from the same up to 4K. And the figure shows that the thread with the large persistent granularity is going to yield higher throughputs because it's going to be prioritized compared to the low granularity thread. So why they need this is
they need it as key because they have to handle the variable size in the data set from 100 byte to what they say based on the observation from the Facebook. Right? 30-some kilobyte to up to very large data.
Yes, exactly.
They need to adjust it.
So the second conclusion is the congestion, and the congestion here is proportional to the total data transmission rate V total. If V total here is greater than Vs, then the thrashing begins, which is a very natural thing to happen. So these conclusions inspired two congestion control techniques. And we said that there's two persistent data flows in BonsaiKV, which is one, the foreground log thread here, which is going to create the log or persist the log from the DRAM to the non-volatile memory. And then we have the background log checkpoint that's going to do NVM to NVM data movement. So this log checkpoint incurs unexpected memory interference for the foreground thread. And they propose a prioritized persistence technique to reduce this interference.
By changing what?
By increasing the granularity of this to make it more prioritized and reducing the granularity.
Instead of changing the priority, they just increase the size.
Yes.
That directly affects the priority.
Yes. So, well, since larger data persistence granularity means higher priority in this case, they will design a private 2 kilobyte volatile log combining buffer. And this, every thread will have this 2 kilo log combining buffer. And it's used to pack the logs with some other data, and they are persisted at once.
Well, what's the triggering conditions to increase or decrease size?
It's not adaptive.
It's not adaptive.
It's not. So just pretty much, okay, we know that the log has more priority and it's smaller. So we're going to pack them and persist them at a higher granularity. But we know the value is bigger, so we're going to slice them and persist them at a lower granularity.
That's the clever thing.
Yes.
Based on naturally known facts.
Yeah.
Observation.
So reducing this thread's data transmission rate, which is the checkpointer thread, is going to avoid the contention. So reducing the data transmission rate per thread, to do that, they need to divide these values into smaller values or smaller sets. They call them stages here. And then they perform the persistence one stage at a time. And since they use xFence to slice them up, then it's going to be executed in order. So another thing they did is that they reduced the number of parallel threads, actually, which is, I don't think it's a optimization, but they mention it. So if they have too much pressure from too many concurrent threads, they just reduce the total data transmission rate by reducing the number of outstanding requests in general. So moving to the data layer, we know that the D nodes are going to be striped across different channels within one node. So this is the optimized data layout that they talk to. So they partition the D node into multiple fixed size strips. This is the D node. It contains multiple entries. So they will partition it and they will add this metadata strip. And they say that for their platform, it's 256 bytes, because they will partition later these NVM nodes into 256 slice or blocks within the non-volatile memory pool. So the total number of strips in one D node is going to be aligned with the number of memory channels per CPU. And the metadata strip is going to contain some fingerprint array, a bitmap, valid bitmap, or other metadata. And the data strip is going to contain entry slots. And the order array here at the end is going to record the D node entry order here within the entries that were striped across these data stripes. So each non-volatile memory device is going to have a memory pool that is partitioned into the same granularity blocks to store either a metadata or a data strip. And strips belonging to one D node are going to be spread randomly across all non-volatile memory devices within one NUMA node. So they will be like, okay, which NUMA node is getting, or which device is getting the most contention? This one? Okay, I'm gonna insert here. And then to avoid interference. So how do they perform a lookup on this architecture? Is a D node lookup is gonna need to find a metadata and a data strip. So the first one, let's say. And these ones are going to maybe be located in different devices. So each node is going to have a D node ID we talked earlier. And this D node ID has a a 4-byte, or it's totally a 4-byte, but it's split into a 3-bit NUMA memory node ID and a 29-bit strip index. So first, the thread is going to locate the memory node, and then it's going to use the hash strip index to find the strip permutation array entry. These selectors are replicated across the nodes, so they are available.
So when they find in the node or the data from the stripe disk, based on the indirection mapping layer, whether which way I should go.
Exactly.
Stripe set I should go.
Yeah. So this node ID is going to tell us which
node I have to go, and inside the node, and which stripe.
Exactly. So the stripe index is going to go a selector, and we know that the metadata is in NEF5.
Why they use that large bits for stripe index? Stripe index is not used.
It's going to index this space. So it's going to tell us, the stripe index is going to tell us where in this NUMA node our metadata is.
So it's natural if you have your own node ID or key ID, then you just can get stripe ID by applying the multiple operation divided by the stripes aside. Right? So it's a simple calculation. Then why do we need 29 bits? Is it 29 bits?
It is 29-bit. I think because this is a DRAM structure.
DRAM structure.
I mean, it is persistent because of the dnode ID, but it is looked up. Means like they have a copy in the DRAM that they're going to use for lookup. And then the stripe index is going to lead us to the metadata first, or the metadata stripe. And then this metadata stripe is going to be copied to DRAM, so we don't have to look for it each time. So once it's copied to the DRAM, they use this information or the fingerprint within the metadata stripe to find which my entry or my key within which data stripe is going to be. And then it goes back here. Okay, we're going to find it in here, D3. D3 is in NBM1. So they use the stripe index to find the entry within NUMA1 and NBM1.
So explain it once more using 1, 2, 3, 4 in this figure.
Okay, so first they use this ID to, sorry, I think you can't see here. One, find the NUMA node, and then find the device within that node, and then take those to locate it, and then use the stripe index to find which slot within that channel. So that's for the channel level parallelism. What about the NUMA level? So for NUMA level, if there is a remote read to a dnode entry, the reader is going to perform something called a hotkey identification. And if it is a hotkey, then the reader is going to copy the dnode entry to their local memory. So if I have, let's say the main is in node 0, and I have a read issued to node 1 on a hotkey, then in that case, it will take that entry and copy it to my own node, but it's gonna copy it in a shadowed layout manner. So to prevent these, because accessing these replicas might require a lot of memory addresses or maintaining multiple memory addresses. To avoid this extra memory usage, they're going to provide this uniform way for threads to find or these threads running on different memory nodes to access the same data from the same location, just the base address.
It also shows you uniform access patterns. So then this approach becomes useless, right?
Yes. So every dnode stripe is going to reside at the same memory offset all the time. So this data replication will require maintaining some coherence between the main data and the replica. So this is the main and this is the replica. So the existing protocols, they will incur some excessive data writes for maintaining the replica coherence, because every time I edit the main, then I'm going to have to update the replica, etc. So they propose a writer optimized self-invalidation protocol to achieve this write optimal data coherence. So they denote an entry as a main or as a replica. So each entry will know if it's a main or a replica. And then each replica here will have a timestamp. And if I fetch this replica at this time and the timestamp has passed, then this replica becomes expired and no readers can read it from here. So if I need it again and it's still hot, then I'm going to have to prefetch it again. So this gives a little bit of concern, because what if it has been modified along this time? So within this time that it's still valid here, but it hasn't been invalidated, but it has been written to the main. So what do we do then? So this is going to cause some low writer performance, because the writer is going to have to wait until that one is invalidated. But why they call it write optimized is because they leverage the log layer here to separate this new data write from the older data version. And for example, here, although there is a replica for the main in the data layer, the threads can still write the new data into the log. And then BonsaiKV is going to perform the index tier modification. So all of the incoming reads are going to find this entry from the log, but all of the older reads that have been issued can still read it while it's still valid. Another issue is the log checkpoint. So what if I have some information in the log, but it's going to be checkpointed to the main in a D node? So that's going to cause a problem. So then we have a new log here, and then a checkpoint begins. If we flush the log to the main, but the replica is still valid, then it's going to cause the data version conflict between the main and the replica. So what they do is they just create this time interval between the log checkpoint and the log start. And they set this period to longer than this period. So we know that, let's say the log started here, but I cannot checkpoint while it is valid. I have to checkpoint at least a little bit longer than the validity period. So as soon as this one becomes invalid before another.
It's not called the validity period. It's called grace period. Right? That's a common general term. The grace period. While I'm working on and the other guy is still, holding the reference to the old value, I cannot recycle it, right?
Yeah.
So I have to wait gracefully until all the guys holding the old reference go out.
Yeah.
Right.
So they just set this delta big T as longer than that value, so to prevent it from happening. Let me go through the evaluation. So this is a setup. They have 2 nodes and 6 non-volatile memory channels in each, 128 GB of DRAM, 6 in each node. So they compare the system with some legacy systems, and they use the YCSB workloads. So they evaluate the performance and the DRAM consumption of the 3 variant collaborative tiered indexing. So all the variants use the same mastery implementation. And then the first approach, they call it BonsaiKV DRAM only, but it's just mastery. The second approach is mastery plus data offload using the shim layer. And then the third approach is data offload plus uploading that metadata, like we said earlier, that metadata stripe, we bring it and then we use it to, we don't have to look it up each time. So the experiment is YCSBC, and the workload is 100% get, and each thread before is going to insert 150 million 16-byte records. So offloading the index from DRAM to NVM is going to degrade the performance here, or the throughput, by 44%. But retaining the related metadata in the DRAM is going to close that performance gap and is going to deliver similar performance as the DRAM only approach. I was wondering why they're indexing in the NVM, but it's still performing better than DRAM. I think it's a little bit biased, because mastery in the leaf node, they have some linear search within the keys. But they use that fingerprint. So using the fingerprint to form an O1 lookup is going to accelerate the search and make this slightly better than using mastery only. So in this lower part, the DRAM only indexing, they say it causes heavy memory pressure, and indexing 3.6 billion 8-byte key value pairs is almost 53 gigabytes of data in general. So this consumes 107 gigabytes of DRAM, which is much more than what they mentioned earlier with Facebook. It's maybe like double. So the size of the mass tree is double the size of the data. When I looked into the mass tree paper, it's expected to yield maybe 15 to 20% maximum the size of data. But so I don't know what they did to make it double, honestly. So they say that in contrast, BonsaiKV data offload, which is this one, data offload, but they don't bring the metadata for faster lookup. So every time they have to look for the metadata. So this solution only costs 8.3 gigabyte of DRAM over 53 gigabyte of data. And then the other one, if they bring the metadata, this metadata itself is going to consume 7 gigabytes, so around 15 gigabytes. So it's around 20%, let's say 20 to 30%, is it, of the total data set? Honestly, this is a confusing part for me because their claim is, well, Facebook is going to bring, let's say 30%, or the size of the index is 30% the size of the data, but our index is slightly smaller. But it's still pretty memory heavy comparing it to the data size.
Data okay, size-wise,
the total data size
memory footprint is significantly lower, right?
It's significantly lower compared to BonsaiKV DRAM only, but BonsaiKV DRAM only is mass tree. And when I looked through the mass tree experiments, mass tree is not supposed to yield this much index size. So that's the confusing part.
So they show what they're supposed to show.
Yeah.
Then, right?
Exactly. So the next experiment is 12 user threads and 6 checkpoint threads in a socket. And then, yeah, they are checking like the prioritized persistence effect. So the throughput increases gradually, and it demonstrates that the log packing will improve the throughput by 5.15 times over the no packing setting due to the zero write amplification and then the reduced number of cache line reads after persist. So this one is the parallelism benefits of the data striping. So they compare BonsaiKV with PackTree because PackTree has a NUMA-aware management or mechanism technique. So they use YCSB-E here with 24-byte key and 8-byte value. So this figure shows that PackTree is unable to fully utilize all the non-volatile memory bandwidth because it's a NUMA-aware, it's not channel-aware, let's say.
That's not because it's NUMA-aware. That's because they actually use small size values.
That is true. So this one is the DRAM versus non-volatile memory consumption of all of the key values, of course. This one loads 5 million 16-byte key value, 16-byte each. And ListDB achieves a constant DRAM consumption for a fixed size lookup. And then FlatStore and Viper, they use 6.7 times to 9 times more DRAM space than Bonsai. And then DP3 is very DRAM frugal because it has like a split tree structure and it has a very large leaf fan out. So it doesn't consume a lot of DRAM. So besides, every log in the ListDB has an 8-byte pointer. So ListDB has the highest memory space amplification, they're saying, but because of that. Viper will consume the smallest NVM space, of course, because they have this like V-page metadata is all offloaded to the non-volatile memory. Also, their index is a hash index. So, yeah. So finally, is say general experimental analysis For load here, BonsaiKV without checkpoint, without interference, is going to scale to the most threads because we don't have the interference. And then here with the interference, it's going to start to slow down the more the parallelism goes. For this one, which is a mixed workload, Viper performs very well because it's a hash index. So it will perform a very fast lookup. For the here too, the DP3 and Viper are hash lookups, so they perform better. And then you have here, which is the scan workload. They say this line pretty much is the the total number of threads per socket. So here we start to experience some overhead from the remote reads. So yeah, it's a very natural result. So the last part is a discussion. Here I thought that they did not achieve what they claimed in their motivation in terms of reducing the total DRAM resident index. It's still high, but they also did not test it with the extreme. Another detail specifically is with realistic workloads, we will have small keys and variable sized values, right? They're going to be from small to large. So the large sized value, the bandwidth contention is an issue. So the staging technique that they did is pretty much effective. But what if we have small sized values? Then in that case, the value persistence priority, it becomes a small concern because they will be pushed back and their data transmission rate is going to be slower. So maybe we're going to have a slower search because the log is going to grow and it's not going to be checkpointed. Also, there's no channel level parallelization because there's no opportunity, let's say, to move the data to the D node to stripe it over multiple devices. So I think this might be I'll say a weakness of that design or something that should be optimized. That's it.
Okay.
Yeah, it's done. Thank you.